Okay, so let's now talk about some of applications of diagonalizable matrices, actually, applications of diagonalizability. Okay. So one basic application of, say, diagonalization is to define the function of matrices, actually. So we have seen that if you have a polynomial p of x, okay, it's like c naught plus so on and so forth, cn x power n, then p of a is a matrix, actually. Okay, so it has a meaning. So you can say that you have c naught I plus so on and so forth, cn a power n. Okay, so for polynomials, it's not an issue. Not an issue. How about if you have a function like e power x, or like you have f of x that is, say, sine square x, actually. Okay, then can we have like f of a as e power a? Can we have f of a as sine square a? So what would be the meaning of this, actually? So I know that p of a is matrix. So if e to the a is a matrix, the question is, what is that matrix? Is sine square a is a matrix? Then how can I know explicitly this sine square a matrix, actually? The answer is, we can do it with the strategy that I'm just gonna drive, actually. Okay? So suppose you have a function f. Okay? Suppose you have a function f that is analytic. Okay? That is, say, analytic, that is, it has a convergent Taylor series. It has a convergent Taylor series, actually. Okay? Like e to the x, like sine square x, and so on and so forth. I want to give meaning to the f of a. Okay? I want to give meaning to the f of a, actually. So if f of x has a series, you can expand, say, f of x in a kind of a Taylor series, say an, some coefficient n, x power n, where n goes to 0 to infinity. So if you can expand f of x in such a convergent series, then what could be the potential meaning of f of a? The potential meaning that we can give to the f of a is going to be the series n equal to 0 to infinity an, where an's are scalars, times a power n. Okay? So if this series is convergent, in other words, if your f is analytic, it has a convergent Taylor series, okay, then this series makes sense, actually. And if this series makes sense, this series of matrices would make sense, actually. Next question. How do I calculate this f of a, explicitly, actually? The answer is the diagonalization of the matrix A is going to help you. Okay? So as A is diagonalizable, I'll assume that the matrix A is diagonalizable. So I know that I can write A as P D, what do you call P inverse? And I can also write, say, A power n is going to be A power n P D power n P inverse. So we saw how to do it. Let's substitute this here in the sum, actually, and let's see what we get. So you have what? Your f of a would be sum that goes from n equal to 0 to infinity in the place of a power n, I can replace this. So I can have a n p d power n and p inverse actually. So that's what you can do. And by, say, distributive law, okay. So you have this series, so the question is how to simplify it further actually. Now, since f has a convergent series, so the convergence of the series means that you can write it as that series as the limit of the partial sums actually. You can write this as the limit of the partial sums. So in other words, I can write this as limit k goes to infinity of sum, say k equal to 0 to n, ak p d power k and p inverse actually. And this sum is a finite sum. So if this sum is a finite sum and p is constant in each of the term actually, so by distributive law you can take these p and p inverse outside of the sum actually. So you can do limit k goes to infinity, and you can write this as p sum k goes to 0 to n, okay, and ak d power k and p inverse. So by distributive law I can apply this sum actually, or I can take out this sum, okay. I can take these p and p inverse outside of this sum actually, okay. I mean, if you haven't still understood it, what I'm saying that all these terms are like a1 p d p inverse plus a2 p d square p inverse up to an p d power n p inverse actually. Now in all of these, what do you call terms, p and p inverse is there. So by distributive law you can pull them out. You can pull them out actually of the sum. So that's precisely what I'm doing here actually. Okay. And if I wish, I can rewrite this series again as, okay, as this infinite series n equal to 0 to infinity ak, you know, an and d power n and p inverse actually. Okay. By the way, why I did these two steps, because I'm not allowed to pull the p and p inverse out of an infinite sum actually. The distributive law works for the finite sum. So I turned infinite sum into the finite sum, applied distributive law of the matrices, and returned back to what you have actually. So what actually I have done from this step to this step, I have just pulled this p and p inverse out of what do you call the sum actually, and the convergence of the series is helping. Okay. Now what would be this? What would be this actually? Let's think about the sum that you have inside the bracket. What is a d power n? The d power n is the eigenvalues associated. So it's the, so what is d? So the d is, take the eigenvalues of the matrix and put it here. So what would be d power n? So it's going to be the eigenvalues power n and 0 and 0 here. Okay, this is what that you're going to get. What would be an multiplied with d power n? So it's going to be an multiplied with these eigenvalues. An multiplied with lambda n power n. Okay. How about taking this sum that goes from 0 to infinity? What would be the meaning of taking this sum? So the meaning of taking this sum that you can give is that, okay, sum all these, sum from 0 to infinity, an lambda 1 power n, and sum n equal to 0 to infinity, an lambda power n, lambda n power n. Okay, this is what that you're going to get. So now, what is f of a? So the f of a is p, this sum multiplied by p inverse, and hence now I can say that f of a is p multiplied by the matrix in which you have this infinite sum n equal to 0 to infinity a n lambda 1 power n up to sum that goes from 0 to infinity a n lambda n power n, okay, 0 on top, 0 below, multiplied by P inverse. So calculate these three matrices, or you can go even one step ahead actually. Okay? You can go one step ahead. What is each one of these history? I mean, what was my f of x? My f of x is a n x power n when n goes to 0 to infinity. So what would be my f of lambda I? So it's going to be a sum that goes from 0 to infinity a n and lambda I power n. Hence, with this recognition, I can say that my f of a is matrix P multiplied by a matrix in which you have f of lambda 1, f of lambda 2 up to f of lambda n, and a 0 matrix here and 0 matrix here, and multiply this matrix with P inverse. So this is a recipe to calculate the, what do you call, the matrix for any analytic function that has a convergent series. So what you can do, take your function, so for a, find the all eigenvalues, you can find it, it's not difficult. Then evaluate the eigenvalues, the f at each of the eigenvalue, and make a diagonal matrix out of it. And using the eigenvectors, compute the vector P and P inverse. And then substitute them and multiply the product. This is going to give you a matrix, and that matrix is going to be f of a actually. Let's do an example. Let's do an example. This one. So here is example. So imagine I have been given a matrix A that is pi and iota pi by 2, negative iota pi by 2, okay, and pi. And I have been said to calculate sine A. The matrix sine A actually. Okay, the matrix sine A. So for this recipe, first we need to recognize what? That my function f of x is sine x. I need to compute the eigenvalues of the matrix A and eigenvectors so that I can make the matrix P and P inverse. And then substituting values here and multiplying the matrices would give me sine A. So let's do it. It is not difficult to see that A has eigenvalues. A has eigenvalues equal to pi by 2 and 3 pi by 2. So pi by 2 is one eigenvalue and 3 pi by 2 is another eigenvalue actually. With associated eigenvectors, okay, associated eigenvectors. So this is like my lambda 1 and this is like my lambda 2 actually. And the associated eigenvectors respectively are V1, which is 1 and iota, and V2, which is 1 and negative iota actually. Okay? 1 and negative iota. Once you have this, what is your matrix? By the way, even if you wish, you can also give this matrix a name actually. So I can say that my f of A is P f of D matrix multiplied by P inverse. By f of D, I mean this. Okay. This. Anyway, so what would be f of D matrix now? So the f of d matrix is going to be f of lambda 1, which is f of pi by 2, 0, 0, and f of 3 pi by 2. And what is f of pi by 2? So what is sine pi by 2? So sine pi by 2 is really sine pi by 2 is 1, 0, and sine 3 pi by 2 is negative 1. So this is my f of. What is my matrix P? So the matrix P is that, okay, take these eigenvectors and put them in here. So 1 and iota and 1 and negative iota. You can easily calculate its inverse. The inverse would look like what? So it's going to be 1/2 minus iota by 2, 1/2 and iota by 2. So this is the P inverse. Okay. Now we have everything to calculate f of a. So what would be the sine a? So sine a is going to be the product of three matrices: 1, 1, iota, negative iota, times 1, 0, 0, negative 1, times 1/2 negative iota by 2, 1/2 and iota by 2 actually, and hence now you have this matrix sine A. So you can multiply these three matrices and you can get a matrix. A very interesting thing actually, that now you are able to define what is meaning of the matrix sine A actually, and sine A is going to be the matrix 0 minus iota, iota and 0. Calculate these three and you have it. So in your exercise sheet you need to maybe calculate some of such matrices actually. Okay. What is next? So this is one application. So according to this application, you can take any analytic function which has a convergent Taylor series, and you can define a matrix associated with that function actually. In other words, you can define f of a matrix for such function, and which is a huge leap actually. Okay? In other words, you can start doing the calculus of the matrices actually. So if you have now f of a, you can think of asking, okay, what would be the derivative of such matrices actually? Okay, if they are if the a is time dependent. Anyway, so it's really a new beginning. It's really a new beginning actually. What is the next and last application that I would like to discuss is basically solving the system of ODEs actually. Okay, so using this you can solve some of the system of the differential equation. Okay, so I hope you have solved such differential equations like, okay, dy by dt equal to some function of x and y, something like first order simple differential equation. The question is, can we solve a system of differential equation? The answer is yes, using this actually. So consider a system of differential equation. Consider a system of ordinary differential equation that goes like du by dt equal to au. Okay? And where A is a matrix actually, A is an n by n matrix, okay, and U is a vector actually that has components. So U1, U2, Un, where these components are functions of time, okay, they are the functions of time. And imagine I have been given an initial condition that initially this u was a vector u naught. Okay, it was a vector u naught actually. This is not one equation. It's like you can have the hundreds of linear differential equations sitting in this side, inside this actually. Okay. Now, once you have this system of differential equation where A is matrix, then the solution of this system of differential equation can be defined as a function u of t, which can be explicitly written as this. Then the solution of this system, let's call this system a star, okay? Solution of this system star is a matrix actually, is a vector u of t that you can obtain through E by computing the matrix E to the AT and multiplying it with your initial condition u naught actually, okay? And multiplying it with u naught. So this is going to be the solution of this system of differential equation actually, okay? But this would work provided, this all theory will work provided A is diagonalizable actually. Okay? A is diagonalizable. If A is diagonalizable and you have such a system, you can find its solution by computing the matrix E to the TA and multiplying it with u naught. So let me do one example based on it. Let me do one example based on it, and you can see that how interesting this works. So consider a differential equation that goes like dx by dt, and it has values x plus 4y and dy by dt, and it has equation x plus y, and imagine I have been given some condition x of 0 equal to 1 and y of 0 equal to -1. Let's write first this in matrix form. Let me define u, vector u of t, as the vector x of t, y of t. Okay? Then the du by d vector and the du by dt vector is going to be the vector comprising of dx by dt and dy by dt. Okay? Let's take the matrix A as the coefficients matrix. So first I'm going to take the coefficients of x. So what are the coefficients of x? So it's 1 and 1. And the coefficients of y are 4 and 1 actually. Okay? So if u of t is this, what would be u of 0? The u of 0 is going to be x of 0 and y of 0. And x of 0 is 1 and y of 0 is -1. Okay? X of 0 is 1 and y of 0 is negative. Then now I am in position to write this system of differential equation in a matrix form actually. I can write it in a matrix form. So in other words, I can say that I have du by dt equal to au. Does it make sense? Take this vector dx by dt and dy by dt and equate it with the matrix 1, 4, 1, 1 multiplied by x of t, y of t. X of t and y of t. Okay? Then take this row multiplied with this and equate it to the first value, you're going to get the first equation. Take the second row, multiply with the x of t, y of t and equate it with the second value, you're going to get the second equation. So you can write this. So in other words, this is a correct format of putting this differential equation into a matrix form, and the initial condition of this is this vector 1 and -1. Okay? For this system, I know already the solution actually. What is this solution? Take this u naught, which is this vector, and multiply it with the matrix e to the ta, at. So this means that I need to now compute the matrix e to the at actually. I need to compute, so my function is really like e to the, I don't know, ex, okay, and I have to compute f of a, which is e to the ta, e to the t. But this is going to make sense only if the matrix A is diagonalizable actually. Okay? The matrix A is diagonalizable. How can I know that matrix A is diagonalizable? Take the matrix A, what is the matrix 1, 4, 1, 1, and compute its eigenvalues. So what you can do, in other words, you can compute its characteristic polynomial, and it turns out its characteristic polynomial is like x plus 1 times x plus 3. So this means that this polynomial has two eigenvalues, one is -1 and other is -3 actually. Okay? And corresponding to the lambda 1, say there is you can compute what you call the eigenvector. You know how to do it actually, so I'm not gonna get into these basic calculations. So the eigenvectors associated with this is -2, 1, and the eigenvalue associated with the eigenvalue -3 is you can say 2, 1. You may interpret these two vectors that these two vectors are the vectors that are spanning the eigenspace of the matrix A associated with these two, eigenvalues actually. So you have it. Once you have it, this means that you have your matrix D actually. You have your matrix D. So what is your matrix D? -1, 0, 0, -3. And you have your matrix P, which is just take these, put them in column vectors actually. So 2, 1. This is what is your matrix P. You can easily calculate what you call these two vectors, the inverse of it. Okay, the inverse of this matrix, when you will compute it, is going to be, I don't know, it's going to be -1/4, 1/2, and what do you say? -1/4, 1/2, and 1/4 and 1/2. This is going to be P inverse. So if I compute e to the TA, in other words, if I compute e to the TA, I need to do what? I need to take my matrix P, which is -2, 1, 2, 1. I need to calculate e to the TD actually. Okay, so instead of A, I'm going to do, in other words, e to the TA is going to be the matrix P, e to the TD, P inverse. What is matrix P? P is -2, 1, 2, 1. E to the TD is, okay, take the eigenvalues and substitute it in the place of the D actually. So the first eigenvalue is 1, -1, so it's going to be e minus t, 0, 0, and e to the -3t, multiplied by -1/4, 1/2, 1/4, and 1/2. So this is what that you're going to get. And once you have this, you can multiply all these three matrices and you can get e to the TA. And the matrix that e to the TA that you're going to get is going to look like this actually. Okay, just writing it directly. E to the -t divided by 2 plus e to the 3t divided by 2 negative e to the t, -t plus